Welcome to G Fun Facts Online. Today, we're journeying into a world that exists right now, inside all of us. Imagine a future where healing isn't about pills or invasive surgery, but about swarms of microscopic robots, each no larger than a single cell, navigating our bloodstream to mend us from the inside out. This isn't science fiction. This is the dawn of a new medical era, powered by the gentle and non-invasive force of sound. This is the world of sound-controlled microrobotics. The idea of sending tiny machines into the body has been around for decades, but moving from fantasy to reality required combining progress from several different fields. Miniaturization from microelectronics gave us the tools to build small things. The field of microfluidics taught us how to handle tiny amounts of fluid, crucial for navigating the body's internal rivers. And a 19th century concept called acoustic levitation, the ability to suspend objects using sound waves, provided the final piece of the puzzle. The convergence of these fields set the stage for the healing swarms now on the horizon. So how do you command an army of microscopic machines deep within the body, without wires or tethers? The answer is ultrasound, sound waves with frequencies too high for us to hear. This technology is a cornerstone of a field called acoustofluidics. The primary force at play is the acoustic radiation force. When a sound wave encounters an object, it exerts a small but significant push. Think of it as the pressure of sound. By carefully shaping the sound field, scientists can create invisible acoustic traps that can hold a particle in a specific location, or push it along a desired path. These tools are often called acoustic tweezers. There are two main types. Standing wave tweezers use the interference of two opposite sound waves to create stationary points of high and low pressure, trapping particles at these nodes. By shifting the waves, you can move the trapped particles. Traveling wave tweezers use a single, focused, corkscrew-shaped sound beam. This vortex creates a pressure low point at its core that can trap a particle, which can then be steered in 3 dimensions. The great thing about acoustic tweezers is that they are non-invasive and don't harm living cells. But holding a robot is one thing, making it move is another. For that, many of these micro-robots use a surprisingly elegant engine, a bubble. By designing a micro-robot with a tiny cavity that traps a bubble of air, it can be turned into a microscopic jet ski. When an external ultrasound field hits the bubble, it makes it oscillate incredibly fast. This rapid vibration creates a powerful streaming flow in the surrounding fluid, which propels the micro-robot forward. It's a remarkably efficient way to swim at the microscale, where the world is thick and viscous. By tuning the ultrasound, researchers can turn these tiny engines on and off, or even steer them by activating different bubbles on the same robot. While a single micro-robot is impressive, their true power is unlocked when they work together as a swarm. Inspired by ants and bees, swarm robotics focuses on coordinating large numbers of simple robots to achieve complex tasks. A swarm can deliver a much larger payload of drugs, cover a larger area for diagnostics, and is more resilient. The failure of a few robots doesn't mean the mission fails. The hallmark of a swarm is emergent behavior. This means complex, group-level actions arise from the simple, local interactions of individual robots, without a central controller. By equipping each robot with a tiny sound emitter and detector, they can talk to each other, coordinating their movements and dynamically changing their formation to navigate complex environments. Some researchers are even developing self-healing swarms, where the group can identify a faulty robot and ignore its data, or even physically reconfigure to repair damage. This ability to self-organize and adapt is what makes swarms so powerful for use inside the unpredictable environment of the human body. So what can these healing swarms actually do? One of the most promising near-term applications is targeted drug delivery. Many potent drugs, like those used in chemotherapy, are like sledgehammers. causing severe side effects because they harm healthy cells along with the diseased ones. Microrobots are a scalpel. They can be loaded with a therapeutic payload, guided through the bloodstream to a tumor using ultrasound, and then another burst of sound can trigger the release of the drug right where it's needed. In a study on mice, bioabsorbable acoustic microrobots loaded with a chemo drug were guided to bladder tumors, significantly reducing their size with minimal side effects. Beyond drug delivery, microrobotics is set to revolutionize tissue engineering. Building new tissues requires precisely manipulating individual cells. Gentle acoustic tweezers are perfect for this. Researchers have already demonstrated 3D printing with living cells, picking them up and placing them in specific patterns. One day, this could be used to assemble a patch of heart muscle to repair damage from a heart attack, or construct new cartilage to treat arthritis. Another incredible frontier is nerve regeneration. Damage to our peripheral nerves can be devastating, and natural repair is slow and often incomplete. Research has shown that low-intensity pulsed ultrasound can stimulate and accelerate the regrowth of nerve fibers. A swarm of microrobots could be guided to a nerve injury to provide localized, sustained ultrasound therapy, promoting faster and more complete recovery. The potential is vast, with other research exploring using swarms to break up blood clots, perform biopsies without surgery, and even capture and remove toxins from the blood. But the human body is a chaotic and complex environment. You can't just pre-program a route and hope for the best. This is where artificial intelligence comes in. By integrating AI, we can move towards true autonomous behavior. An AI-powered navigation system can use real-time ultrasound images to identify obstacles and plan the optimal route for a swarm. It can dynamically control the external fields to change the swarm shape, allowing it to squeeze through narrow passages or spread out to cover a wider area. This makes the system adaptable, precise, and autonomous, reducing the need for constant human control. Of course, you can't just inject tiny metal robots into a person. The building blocks of these inner healers must be carefully chosen. They must be biocompatible so they don't provoke an immune response, and often biodegradable so they safely break down and are eliminated from the body after their mission. Researchers are using materials like hydrogels, which are soft and tissue-like, and biodegradable polymers already used in things like dissolvable stitches. Manufacturing these objects, measured in millionths of a meter, requires specialized techniques like photolithography from the microchip industry, or an advanced 3D printing method called two-photon polymerization, which can build incredibly complex 3D structures with sub-micrometer precision. While this future is incredibly exciting, the path to the patient's bedside is still filled with challenges. Controlling and imaging these swarms in deep tissue is a major hurdle. Ultrasound weakens as it travels, and there's a trade-off between penetration depth and control precision. Real-time tracking is also difficult, as current imaging technology struggles to resolve such tiny, moving objects. And then there is the question of scale, going from a few robots in a lab to manufacturing and controlling billions for a clinical application. Beyond the technical hurdles, we must also navigate the ethical landscape. How do we ensure a patient gives truly informed consent for a treatment involving autonomous robot swarms? How do we protect the privacy of the sensitive biological data these robots could collect? And if an autonomous swarm makes a mistake, who is responsible? The surgeon, the manufacturer, or the AI programmer? These are profound questions that require a broad public dialogue to ensure this technology is developed responsibly. The journey into the microscopic realm has just begun, but the promise of sound-controlled microrobotics is undeniable. This is a paradigm shift in how we think about healing. A future where cancer is treated with a surgical strike, not a systemic bombardment. A future where damaged nerves are regenerated and new tissues are built cell by cell inside the body. The robotic swarms that will heal us are no longer a distant dream. They are taking shape in labs around the world, and they promise a future where medicine is more precise, less invasive, and more effective than ever before.